It's funny how we treat the walls of our homes, like they're just static barriers.
Right.
You hang a picture, you paint them, maybe lean a bookshelf against them.
Mm.
But if you actually peel back that drywall, you realize the house isn't a box. It's a machine, a very wet, pressurized, chemically reactive machine.
It's an organism, really. You've got a circulatory system, a waste removal system, and a whole nervous system of wires.
Yeah.
And just like a biological body, the tolerances for things going wrong are, well, they're surprisingly tight.
That's what struck me about the source material we're looking at today. We're breaking down this technical walkthrough from Claude Taylor. He's a master builder featured on the How to Plumbing podcast. And he's walking us through a rough end, which is that critical stage where the skeleton is up, the pipes are being run, but nothing's closed up yet.
This is absolutely the make or break moment for a building. And Claude is dissecting a specific project here. It's an 8x8 platform mock-up, and it combines a bathroom, a laundry setup, and a kitchen all in one wall. So it's a density test. He's packing a lot of functionality into a very, very small footprint.
And what I found so fascinating is that even though this is just a mock-up, I mean, it's a display piece.
Yeah.
The physics he's dealing with are completely universal. We aren't just talking about connecting pipe A to pipe B. We're really talking about three fundamental enemies of plumbing.
Yeah.
Stagnation, pressure, and corrosion.
That is a perfect way to frame it. You're fighting gravity to get waste out. You're fighting momentum to keep the pipes from shaking apart.
And chemistry.
And you're fighting chemistry to keep the water inside the copper.
So let's start with that first one, stagnation, the drain system.
Yeah.
Claude is working in this tight floor joist system trying to run a 2-inch laundry line. And he introduces a specific component that seems kind of trivial at first glance, but is actually doing a lot of heavy lifting, the Street 45.
The Street 45. It's one of those fittings that, well, it really separates the DIYer from the pro. If you go to a big box store, you usually see standard fittings with hubs on both ends.
Meaning the pipe slides into the fitting.
Right. A street fitting is different. It has one male end, so it's the same diameter as the pipe, and it's designed to slip directly into the hub of the next fitting.
So it's a space saver.
It is, but it's more about the geometry of the flow in a confined space. When you're working between floor joists, you don't have the luxury of these long, sweeping turns.
You've got, what, 14 inches?
Maybe. The Street 45 lets you stack fittings. So you're literally turning immediately out of one and into another without that intervening inch or two of pipe.
Which implies that every inch of pipe you save isn't just about clearance. It's about maintaining the gradient, right? If you extend the run, you lose vertical height.
Exactly. In drainage, height is currency. You spend height to buy distance, and if you burn up all your height with bulky fittings, you just run out of room to slip the pipe properly.
And that brings us to the most critical part of this whole drain discussion, the slope itself.
Yes.
This was the part where my intuition was completely wrong. My assumption has always been, steeper is better. If you want the waste gone, build a water slide.
Sure, that makes sense on the surface.
But Claude was incredibly specific about checking his torpedo level for a slight 1/8 bubble.
This is the really counterintuitive physics of carrying solids. We aren't just moving water, we're moving water mixed with solid waste paper, organic matter, you name it.
Right.
If you pitch the pipe too steeply, say a 45-degree angle, the water acts like a flash flood. It rushes down the pipe instantly.
But it leaves the heavier solids stranded behind.
Yeah.
The water outruns the cargo.
Precisely. The liquid separates from the solids dry out, they pile up, and eventually you've got a rock-hard clog.
And if it's too flat?
Too flat, the water moves too slowly to scour the pipe, and the solids just settle out like silt in a river delta.
So there's a very specific hydrodynamic Goldilocks zone.
There is, and that's what the torpedo level check is all about. A standard level has 2 lines for the bubble. If it's centered, you're flat. Claude is looking for the bubble to be slightly off-center.
Just touching the line.
Just touching the line, which indicates a roughly 1/4 inch drop per foot of run. And that creates a flow velocity of about 2 feet per second.
2 feet per second, that's the magic number.
That is the velocity you need to keep solids suspended in the flow. It's fast enough to carry the waste, but slow enough that the water and waste stay together as like a cohesive unit.
It's just amazing that a little plastic bubble is the only thing standing between a functioning home and a sewage backup.
Pretty much.
Now, complicating this drain situation is the laundry machine. Claude makes a point of separating the laundry drain from the tub and toilet drains to avoid what he calls wet vent overload.
This is where we have to look at the energy difference between fixtures. A bathtub or a toilet drains passively. Gravity does the work.
It's a gentle flow.
It's a gentle atmospheric flow. A washing machine is totally different. It has a mechanical pump.
It's actively pushing the water out.
Aggressively. It's injecting a solid column of water into the pipe under pressure. If you think of the pipe as a highway, the toilet is a car coasting downhill. The washing machine is a semi-truck barreling down the on-ramp at 80 miles an hour.
And if they share the same ventilation pipe.
The truck takes up the whole road. The laundry discharge fills the entire diameter of the pipe. And as that slug of water moves, it acts like a piston.
Right.
It pushes air ahead of it and pulls a vacuum behind it. And if that vacuum passes the connection for your toilet or your tub, it will literally suck the water out of the P-traps.
So you walk into the bathroom and smell sewer gas because the water seal is gone.
That's it. The wet vent, which is just a drain pipe that also lets air travel up to another fixture, it just can't handle that volume.
So he's building an express lane.
He is. It's a dedicated express lane for the laundry, so its turbulence doesn't mess with the delicate atmospheric balance of the bathroom. It's managing air as much as water.
Before we leave the drainage section, I want to touch on one detail that felt like a masterclass in risk management.
Oh, yeah?
The toilet flange. He installs it, but he doesn't glue it.
The floating flange? This is pure experience talking. The flange is the connection point for the toilet. If you glue it permanently to the subfloor now,
You're committed.
you are committed to a specific floor height. But maybe the homeowner decides later they want thick slate tile or heated floors, or maybe just thin vinyl.
And if you've already glued it flush to the wood, and then you add an inch of tile,
You're in a lot of trouble. Your flange is now sunken. You have to use double wax rings or these precarious extenders to get the toilet to seal, and those are just prone to leaking.
so by leaving it unglued,
He can pull it up later to match the exact finished floor height. It's admitting you don't know the future, so you build in adaptability.
which is a great segue to the supply side, because that's all about preparing for a violent future.
It is.
We're moving from drains to the pressure lines, the copper.
Yeah.
And immediately we run into a material choice. Type M versus Type L.
This is a classic budget versus longevity debate. In the U.S., these are the two most common thicknesses of copper pipe.
Same outside diameter, right?
Same outside diameter, so they fit the same fittings. But Type M, which you can think of as minimum, has a thinner wall. Type L is thicker.
And Claude used Type M for this project because it's a display, and frankly, copper is expensive.
It is.
But he warned against using it in a real home. Is that just because it's physically weaker? Are we worried about it bursting?
Rarely bursting from pressure. Copper is incredibly strong. The issue is corrosion. Water is, it's the universal solvent. And depending on your municipality, your water might be slightly acidic or have high mineral content.
So it's eating the pipe.
Over time, that water essentially sandblasts the inside of the pipe or chemically eats it away. It's eroding from the inside out. And if you have a thinner wall Type M, that erosion process reaches the outside surface much, much faster. You get pinholes, tiny needle-sized leaks that just spray mist inside your walls.
Which you often don't discover until the mold has already taken hold.
Correct. Using Type L is basically buying extra sacrificial metal. You're paying for a thicker buffer zone that might add 20 or 30 years to the lifespan of the system before those pinholes form.
So Type L is the insurance policy. But even the best pipe can be destroyed if you don't respect the physics of moving water. This brings us to water hammer.
Yeah.
We've all heard it, that bang when a valve closes. But Claude treats this as a serious structural threat.
It is. You have to realize that water is heavy. A gallon weighs over 8 pounds. So if you have water moving at 5 feet per second through a pipe, it's carrying significant kinetic energy.
It's like a freight train.
It is. And when a solenoid valve-like in a dishwasher or a washing machine snaps shut instantly, that water has nowhere to go. It's a car crash.
And you get a shockwave.
A hydraulic shockwave. The energy doesn't just disappear, it rebounds. It creates a pressure spike that can be 3 or 4 times the normal line pressure. And that shockwave travels back down the pipe, searching for a weak point.
It's stressing the joints, rattling everything.
Rattling the hangers, stressing the solder joints, and eventually it can crack fittings.
So how does the air chamber Claude installed fix this? He puts in these 18-inch vertical pipes that just end. They don't go anywhere.
They're dead ends, and that's the whole point. When you turn the water on for the first time, Water fills the horizontal pipes, but air gets trapped in those vertical columns. And air is compressible, water is not.
So it's a shock absorber.
Exactly. When that high-speed water slams into the closed valve, the shockwave hits that cushion of air, the air compresses, absorbs the energy, and then gently expands back.
It turns a violent crash into a soft bounce.
It effectively gives the water a place to break without hitting a brick wall. Now, I will mention that in modern residential codes, we are moving toward mechanical arresters.
Little pistons, right?
Yeah, which are like little pistons with sealed air chambers because the air in a simple pipe can eventually dissolve into the water. But the physics principle in Claude's rough-in is absolutely sound. You have to manage the momentum of the fluid.
Okay, so we've handled the flow and the pressure. Now we have to talk about how we actually stick these things together. The art of the joint. I was surprised by how much emphasis Claude put on the preparation, specifically reaming the pipe.
This is the step most people skip, and it is fatal to a plumbing system. When you cut copper with a rolling cutter, you're pressing a steel wheel into the copper. It doesn't remove metal, it displaces it. So it rolls the edge inward, creating this sharp ridge on the inside of the pipe.
So the diameter at the cut is actually smaller than the pipe itself.
Yes, but the real problem is turbulence. That sharp ridge acts like a little ramp. As water flows over it, it creates a chaotic swirl, a localized eddy current right behind the joint.
Like a rock in a stream.
Exactly. And that turbulence creates cavitation, tiny bubbles that implode against the metal. It creates a localized erosion effect. So if you don't ream the pipe, if you don't scrape that ridge off and make it smooth,
You're building a drill.
you are essentially building a drill that will bore a hole in your pipe just downstream of every single fitting.
That is wild. You could do a perfect solder job on the outside, but if you didn't ream the inside, you've built a timer into the system.
It's invisible failure in the making.
Speaking of the solder job, let's talk about the heat. Claude's rule is heat the fitting, not the pipe. To a layperson, you're trying to melt the wire, so wouldn't you point the torch at the wire?
That is the instinct, and it results in what we call a cold joint. Soldering isn't like gluing, it's a metallurgical bond. You need the solder to be wicked deep into the gap between the pipe and the fitting.
Capillary action.
Right. But capillary action only works if the whole environment is hot enough to keep the solder liquid. If you heat the fitting, the heavier mass of metal, it radiates that heat inward to the pipe. When you touch the solder to the joint, the copper itself melts the solder, not the flame.
So the solder follows the heat.
It does. It gets drawn into the joint. If you just melt the wire with the torch, it just kind of globs onto the surface. It looks okay from the outside, but inside the joint is empty. It'll leak immediately.
Claude also dropped a safety tip here. Solder off wood, which sounds like common sense. Don't burn the house down. But he suggests pre-assembling complex sections on a bench.
It's all about control. If you're soldering a complex valve assembly while you're standing on a ladder, reaching into a wall cavity, worried about scorching a stud, you're going to rush.
You'll make mistakes.
You'll make mistakes. If you build it on a workbench, you can make sure every joint is perfect. Then you bring the whole assembly to the wall and make just one or two final connections. It's safer, but it also just yields a higher quality product.
Once that assembly is in the wall, we hit the final boss of plumbing chemistry. Electrolysis.
Oh, yeah.
Claude has a hard rule. No steel touching copper.
This is galvanic corrosion. And it's arguably the most insidious enemy because it is so slow and so silent.
Why can't they touch? They're both metals.
They're dissimilar metals. Every metal has a specific electrical potential, and copper and steel are pretty far apart on the galvanic scale. When you put them in contact and you add an electrolyte, which can just be humidity in the air,
You're making a battery.
you are creating a literal galvanic cell, a battery. Electrons begin to flow from the anode to the cathode, and in this pairing, the steel strap or nail will usually degrade, but the reaction also creates byproducts that corrode the copper. The pipe will weaken at that exact contact point.
So you could have a pipe that lasts 50 years, but because you used a 10-cent steel bracket, it fails in 5.
That is exactly what happens.
Right.
That's why Claude insists on copper-coated nails, copper straps, or plastic clips. You have to break the electrical circuit.
The final safeguard in this rough-in is super low-tech, but crucial. The nail plate?
The armored shield of the rough-in?
It's just a piece of steel hammered onto the stud.
It is, but think about what comes next. The plumber leaves, the drywall crew arrives. They're paid by the sheet, they're moving fast, driving screws every 8 to 12 inches, and they cannot see where the pipes are.
It's a game of Russian roulette with a screw gun.
Without nail plates, it absolutely is. If a pipe passes through a stud and a screw misses the center of that stud by half an inch, it goes right into the water line. The nail plate is there to physically stop the screw. The driver feels the resistance.
The screw won't go in.
It won't go in, and they know to move over.
And what happens if you don't use them?
Sometimes nothing. Sometimes a massive leak immediately. But the worst case is the slow bleeder. The screw punctures the pipe but stays in the hole, plugging it, mostly. A year later, the screw rusts out, and suddenly you have water pouring into your wall cavity behind the finished paint.
It seems like the recurring theme here is that the rough-in is really a time capsule. You are sealing all these decisions behind a wall, just hoping you don't have to see them again for decades.
That is the essence of the trade. Plumbing is an invisible infrastructure. When we look at Claude's mock-up, we aren't just seeing pipes. We're seeing a strategy to mitigate failure. He's sloping the drains to prevent stagnation.
He's adding air chambers to handle pressure.
He's separating metals to prevent chemical suicide. He's reaming the pipes to prevent turbulence. It's a layered defense system.
And that's why the rough-in is the most important inspection. Once the drywall is up, the tile is set, and the paint is dry, all of this engineering becomes a secret.
And if it's done right, you never think about it again. If it's done wrong, it becomes the only thing you think about.
It certainly makes you look at a blank wall differently. You realize there's a whole dynamic, violent chemical drama playing out just on the other side of the plaster.
And it all relies on those initial decisions. That 1/8 bubble, the type of solder, the separation of the laundry line.
Well, I, for one, am going to go home and check if my washing machine causes my toilet water to move. That piston effect is going to haunt me.
It's a good diagnostic to check.
Thank you so much for breaking this down with us. It's amazing how much complexity is hidden in such a, standard system.
Always a pleasure. It's the details that make it all work.
And to everyone listening, here's a thought to take with you. We spend this whole time discussing how we build systems like air chambers and nail plates to protect our infrastructure from itself, to protect the pipes from their own pressure and from the people building around them. It makes you wonder, what other invisible safeguards are operating in your life right now?
That's a deep thought.
Whether it's in your car, your computer, or even the power grid, what are the silent systems taking the hits so you don't have to? We rely on a lot of invisible armor, something to think about next time you turn on the tap. Thanks for joining us on The Deep Dive. We'll catch you next time.